All right, here we are again, another Monday. So what we're doing now is we are carrying on with confidence intervals, which is chapter 9. And then, of course, chapter 10 will be next, and that will be the last chapter of the course. So let me go open up Moodle and get this open. Now, we started this the other day, but we didn't get that far. It's a fairly complicated topic to explain it, but once you get the hang of it, it's really not that bad. It's just that there's a lot of background that we need to understand exactly what we're trying to do. But once you see what's going on, the actual process is actually not very difficult at all. So let's go to Moodle. And I know we just barely started this, but we can carry on today. And so I did at some point post the actual midterm. When we get there, we'll look at it. As soon as this thing lets me in. All right, here we go. Oops. All right, so way down here at the bottom, you see the midterm is here. And we chose a due date of, what was it? Oh, the 17th. Oh, you got plenty of time. And that means midnight, by the way. It can't really go any much later than that because that's actually the official last day of the class. And they will want the grades a couple of days after that. And that means that unfortunately, I guess the final exam will have to be due, maybe not the 17th, but fairly soon after that. I think that they'll let us have maybe 3 days to get the grades in. I'll have to investigate that because I don't want to miss the deadline. I'll write to the school and ask them exactly how late the grades can be handed in. We have to be careful because, as you know, the semester is going to start. Oh, you know what that reminds me? Yeah, you know, that brings up a good point. I was just looking the other day at the website, and maybe you knew about this, maybe you didn't. But if you look at their academic calendar, here we go. Fall, yeah, this one. All of a sudden, completely out of nowhere. Now look what it says here. Classes begin Monday, January 31st. Now, first things first, the 31st is not a Monday. All right. Let me go get the calendar. Oh, it is. But okay, but the thing is, it was supposed to start on a Wednesday. And originally, now every year that I've ever been at Purchase, the first day of school was the first day after Martin Luther King Day, which is this year is the 17th. So I was expecting to start again on the 18th. And all of a sudden, now it says the 31st. I don't know if they changed that or if it's a last minute thing, but it says here that we're starting up again on the 31st. Okay, so that means that the 17th of January is not, in other words, the school doesn't start this week. So that means that we may be able to have a few more days to hand in the grades. So what I'm going to do is ask the school how late the grades need to be in for the winter session. So I can figure out how much time to give you for the final exam. Let me just make a note of that here somewhere. So it might be possible for you to have a few more days, in other words, past the 17th to hand in the final exam so that they won't be due on the same day. I would prefer it does not work out that way if possible. It all comes down to when they need the grades by. But since we're not starting up again, apparently until the 31st, I would imagine that gives us a little extra time because like I said, normally they would have started the day after Martin Luther King's birthday. So I don't know what happened there, but that's what it says. And okay, I guess we have to stick with that. So, all right, I'll let you know about that. But the midterm, you should have it ready by next Monday, the 17th, and then the due date for the final, I'll announce it as soon as I find out myself. I want to give you as much time as possible, is what I'm saying. All right. Anyway, but beyond that, let's go back to Moodle and go grab our information. So anyway, the midterm is right there. And we have chapter nine problem set to do. Everything else we're done with. Okay. The final exam is actually based just on 8, 9, and 10, because we did everything up to 7 for the midterm. So 8, 9, and 10 are what we need for the midterm. Sorry, the final is 8, 9, and 10. You know what? Let me at least announce that. Hold on 1 second, just to make sure. I will announce the due date. Okay, so in other words, I'm trying to make sure that we don't have to have them both due on the 17th. That's all. All right, so that's taken care of. All right, let's get back to it. Where was I? Okay, there we go. One thing, let me just see something here. No, that's not what I wanted. What the hell just happened? All right, here we go. Let me just save this for today's date. Today is the 10th. All right, anyway, so just a quick reminder, we're creating confidence intervals in this chapter, which basically means you're taking an estimate. For example, X bar is an estimate of the population mean mu. We start that with that, and then we create what's called a margin of error. And that margin of error reflects how much uncertainty there is associated with our estimate X bar. Now, we know perfectly well that X bar is the best way we can use to estimate the population mean, but it's not perfect. You know, it's possible that our X bar is not exactly equal to our population mean. So the question is, how far off is it likely to be? And that's really what this margin of error is trying to capture. So it says here that we did some research on the price of gas in the US, and we came up with a sample mean of 319, which may be exactly equal to the population mean, but it's not likely. It's probably slightly different. The question is, how different is it? And so this margin of error will tell us that basically we're pretty much 95% sure, not completely sure, but 95% sure that the actual population mean is actually somewhere between 299 and 339. Okay, so while 3.19 or $3.19 is our best guess, we know that there's a strong chance that the actual value is somewhere between 299 and 339. So the confidence interval gives us two things. It gives us an estimate of the population mean, but it also gives us a range of possible values, which indicates how likely it is that we're not exactly at 319, but somewhere in this range. So it's a very valuable tool to help us understand, some of the results that we get. We see it in a lot of applications. And so here, though, all we're trying to do is introduce the concept of an interval estimate where we have a range of values rather than a single number. Now, like here's an example that I dreamed up that I think everybody is familiar with. Suppose that you want to know on average how long it takes you to get to school every day. All right. Now, obviously not this class, but for class where you're driving in, and every day you write down how long it takes you to get to school. So for a month, your project is you write down every day how long it took you to get to school. And you do some numbers, you calculate the numbers, and you realize that the mean turned out to be 30 minutes. Now that is our X bar, okay, because the sample here is those 30 days in which you drove to school. The population would be every single time you've ever been to school. All right, so that would be your entire population, but the sample has a mean of 30. So that means it probably is the case that on average, it takes you roughly 30 minutes to get to school. But we know perfectly well that because of weather and traffic and this and that, some days it can take a lot longer, but sometimes it can take less. Okay, there might be days where for some reason there's very light traffic, the weather is nice, and you might be able to get in as early as 20 minutes. But then there's other days where everything goes wrong and it could take up to 40 minutes, let's say. So that 30 minutes, while it's an estimate of our population mean, and it's a good estimate, but it helps us to know what the range of possibilities actually is. In other words, when you're planning to come in, let's say that you find out that 95% of the time, the actual commuting time is between 25 and 35 minutes. And let's say one day you're having a test and you want to make sure that you're not late. Well, then you're going to have to leave the house at least 35 minutes before class time, because you know from experience that that will just about guarantee that you'll be on time. Now, if you're really nervous, of course, you'll leave even earlier. But I mean, the bottom line is the vast majority of the time, you can pretty much count on your time being between 25 and 35 minutes. So if that's the case, what we've actually done here is that 25 to 35 means 30 plus and minus 5, okay? Gives us that range between 25 and 35. And so this is our confidence interval. And we'll explain, by the way, where that 95% comes from. Because it could be something different. We could try 90 or 99, but for now we'll stick with 95 because that's really the most common number that we're likely to use. This is our so-called point estimate, which is just a fancy name for X bar. And then this is our margin of error. Which means that represents how much our commuting time might vary from one trip to the next, 95% of the time. Very occasionally, it could get worse or better. Let's say, for example, one day, there's a holiday where the school is open, but nobody has to go to work. You know, it could happen. And like sometimes, you know, a lot of companies might close for election day, whereas maybe the school doesn't. So there's almost nobody on the road. And you might be able to sneak in under 25 minutes. Or the amount of construction is unusually large one day. There's more than usual, and it takes you 40 minutes to get there. That could happen, but we know that most of the time it'll be between 25 and 35 rather. So that's what this is all about. So what we're really trying to do in this chapter is more than anything else, understand how to calculate this piece, the margin of error. This is easy. We know how to calculate X bar. It's the margin of error that we have to be introduced to now. And that's going to depend on a couple of key factors. Let's see, let's jump ahead. We've done some of this already. So yes, just in general, we have a point estimate plus and minus a margin of error. And by the way, it doesn't have to be X bar. We could do this for any other parameter that we can think of. And in fact, at the end of the chapter, we're going to actually do this for proportions. So we'll start with X bar because that's our point estimate from mu, but we can do the same thing for proportions. And in principle, you can use this for any parameter you need, but in many cases, you will need a different probability distribution to do this. So we'll only be covering the cases of the mean and the proportion, because many of those cases involve the normal distribution, and the ones that don't, we're going to introduce a new probability distribution for those other cases today, I mean. So anyway, what we need to decide right up front before we do anything else is whether or not the population standard deviation is known. Now, even if it's not, we may be willing to live with an estimate of it. In other words, we may say, we know from experience that this should be right around, let's say, X, and we'll assume that that is the correct value. In other cases, we can't really justify that assumption. And in fact, most of the time, we'll find that sigma is either not known or we do not have a proper estimate of it. So what we're seeing here will be used less often. But if we do have a situation like this, we can go ahead and then use the normal distribution for our calculations, specifically the standard normal. You can tell because of that Z there. And so, but what this means is we need to cover a couple of new ideas here. The piece in the box is the margin of error, by the way. So X bar is added and subtracted to this margin of error to come up with our confidence interval. Now the sigma, we know what that means. That's the population standard deviation. The N is the sample size. The subscript for the Z is the mystery element. This is something that we haven't seen before. It tells us exactly what we need to know, but we want to understand what it actually is all about. What does this represent? So first of all, this is the Greek letter alpha, and this is actually going to reflect the confidence we have in our intervals, or the confidence that we're trying to use when we construct our interval, I guess is a better way to put it. Normally, normally when we construct confidence intervals, let me just jump ahead here. We either create a 90% confidence interval, 95%, or 99%. So the relationship between alpha and these three numbers is this. 90% equals 1 minus alpha times 100, which implies that alpha is 0.10. Here, alpha is 0.05. And here, alpha must be 0.01. So in the problem, it may say something like this. You're asked to construct a 90% confidence interval. This alpha parameter would therefore be 0.1, which is the same thing as 10%. Now, what exactly does that mean? All right, well, that's a good question. Let me take out a graph or draw a little graph here so you can see exactly what this is all about. Okay, so let me draw, now I'm assuming that we're looking at the normal distribution, the standard normal that is. And so let's start with 90%. Okay, so this is our standard normal, which we're very familiar with. If alpha is 0.10, alpha over 2 is 5%. The 90% confidence interval will be within this range here. Okay. Or you can call it, think of it as 0.9. These two tails must each contain half of 10% or 5%. So in other words, this is what a 90% confidence interval looks like. It's a range of values, which includes let's think of it as the middle 90% of the distribution. It excludes the so-called tail areas. And because remember, the entire curve has to have an area of 1. If the center piece has an area of 0.9 or 90%, the rest must add up to 10%. And because of the symmetry of the distribution, each of these two areas is equal to 0.05 or 5%. Now, what we're actually looking for is a z-score that corresponds to these areas. So in other words, what do we need to know? In order to look these numbers up, we have to go to our table. And so for this one, for example, let's go to the normal table for a second. Now, in the past, we've calculated a lot of normal probabilities. Okay. And we know how that works. But this time, we're actually working this process in reverse. Okay, so let's do this. Let's look at the negative tail. The area below this z-score is 5%. So rather than looking on the top column, the top row in the first column, we're going to do the opposite. We're going to look for an area of 5% in the body of this table. And you'll see that it's approximately right about here. It's actually halfway between these two values. So if you look here, you'll see that you've got negative 1.604 and negative 1.605. What does that mean? Well, if you average these two out, you'll get negative 1.645 and you'll discover that the probability that z is less than or equal to negative 1.645 is 0.05. Okay. So in other words, in the past, you might have run into a question like this. What is the probability that z is less than or equal to negative 1.645? And that would have been a half. 5%, not a half, 5%. Now we're working it backwards. We're saying, listen, here's an area or probability. What is the corresponding z-score? We need this z-score for our formula for confidence intervals. In fact, this is what we are going to call from now on negative z alpha over 2. And because of the symmetry of the distribution on the positive side, yeah, it's got to be the same number. And if you want to confirm this, you can go to the table and say, listen, what is the probability that this is less than or equal to 1.645? You'll discover that it's it's actually 95 because we're looking at everything below that point. So these are z-scores that correspond to specific areas in the tails. And so this is what you would do for a 90% confidence interval, because we need 5% in the two tails, which implies that the middle piece is 0.90. That's what we want. That's our confidence interval. Everything between these 2 points is our confidence interval. Now, luckily for us, since we're only realistically interested in 3 basic types of confidence intervals, you can actually memorize these. Okay, so in other words, the z-score that goes along with 90% is 1.645, plus or minus, I guess we could call it. So why is that? Again, it's because that means that there's 5% in either tail of the distribution. Now, if we want to do this again with, and you may as well fill this in now. So again, those came straight out of the standard normal table, but we're approaching this in a different way. we're looking in the body of the table for the area that we need and then finding out the corresponding z-score, just the opposite of what we've been doing all this time. But once you discover it, you never need to look it up again. Okay, you could write it down, make up a list, make up a chart, do something. It shouldn't be necessary to keep looking this up because, like I said, we'll be reusing these same three over and over and over again. So why don't we do this? Let's figure out what the corresponding z-scores are for 95% confidence. All right, so let's draw another picture of this. Which, by the way, implies that alpha is 0.05 or alpha over 2 is 0.025. Okay, so let's go to the table. And what we need to do, we'll start with this one. Let's go to the negative z table and look for an area of 0.025. And oh, what do you know? It's right here. So the z-score is negative 1.96. Because the area below that is 2.5%, which is exactly what we need. So therefore, we can come back here and say, oh, this z-score is negative 1.96. This one must be positive 1.96. And if you want to double check it, what you're basically saying is this probability is 0.025. And this probability is 975. That's just a confirmation, but we've done this correctly because we know that the areas that we need are, here's 0.025. Here, because the area in the right tail is 0.025, the area below it is 0.975. So these are our two z-scores when we're constructing a 95% confidence interval. So let's go add that to our chart. And once again, you should never need to look this up again. Great. And then finally, 99%. Now this time, there's very little area in the tails. So alpha is 0.01. And that means each of these tails has an area of 0.005. The center is 0.99. So we have to go to the tables. Now let's go to the negative table and look for 0.005. And unfortunately, it won't be there exactly. But we can find an approximation to it. You see what I mean? It's sort of in this neighborhood. It's somewhere between negative 2.57 and 8. Now this time, it turns out that even though it's hard to tell because of rounding but it's actually slightly closer to 2.58. It turns out that the correct value is 2.576. If you use 2.575, that's fine, but it's actually slightly closer to 2.576. So we'll stick with that. And that becomes our z-score for a 99% confidence interval. Okay, so let's add that to our chart. Okay, so those are the three cases we might encounter in this section of the chapter. By the way, those alphas will prove to be more important in chapter 10 than in 9. I mean, here it just sort of falls out of the confidence interval we're looking for. But it has another very important meaning in chapter 10. So we'll worry about that later. But yes, alpha will prove to be more important than it might seem. So the most important thing is to remember that for each confidence interval or confidence level you might choose, you need to find a z-score. And they come from the bodies of the standard normal table. And they represent essentially boundaries which contain, in this case, 90% of the distribution, 95 and 99. Everything outside of that is the tail area. And so that's this piece. So remember, in the confidence interval that we're constructing, this is what we're looking for. So the z alpha over 2 is the critical value or z-score. This is easy. Sigma, we know, n is the sample size. And this ratio is often referred to as the standard error of X bar, although that's not really that important. The important thing is that this is our margin of error. Okay, that's the important part. And then when we're done with all of this, we're taking X bar and simply adding and subtracting the margin of error to come up with two values. And those two values are the confidence interval. All right, so why don't we jump ahead a little bit here? I've got more discussion here. By the way, if you're using the TI-83 or 84, there's a function in there that will look up these z-scores directly for you. So the instructions are here if you want to read them later on. All right, so finally, we get to do an example. After all that, let me tell you, once you see this example, you'll say, oh, that isn't hard at all. It's not. All this setup is very complicated and abstract sounding. But once you've seen it in action, you'll say, oh, that's not hard at all. So we have a fund with 500 stocks. Now, in this chapter, we will not use the population size. We're going to assume, in other words, we will assume that all samples are small. So in other words, in this chapter, we don't have to worry about the large sample case. It's something that we're sort of glossing it over a little bit here. If we do happen to have a gigantic sample, we can certainly make the adjustments, but we're going to assume that that's not happening here. All right. And that's a constant, by the way, that's a consequence of the fact that we know sigma. So yes, I'm giving you the population size, but we don't really need it in any of our formulas here. So we're going to assume the population standard deviation is 20%. Because that's based on all 500 stocks. The sample size is 10. And the sample mean, X bar, is 8%. So what we're really trying to find out is the behavior of the stocks in the sample, not the entire population, but the sample. So we're going to construct all three confidence intervals for our sample with the sample mean. And in other words, 90, 95, and 99. Okay. Now, of course, don't forget, you already know the three z-scores. So realistically, you should not have to double check. I mean, you can look them up again if you want to, but they're right here. All right, because with that in place, really, there's nothing else to worry about. I mean, that was the only complicated part of this. So here, for example, here's the basic formula. Here's my margin of error. You notice how we've got a z-score, 1.645. And then the rest of them, I just plug them in. Now, this is the result down here. This is the X bar or point estimate. And this is my margin of error. And so what we're seeing here is this is a very wide range. We're saying that we believe that the population mean is 8%, but there's a 95% chance that it's somewhere in this interval between minus 2.4% and positive 18.4%. Now, that's a big range. That tells us that this margin of error is huge. There's a lot of uncertainty associated with these stocks. There's something about them that makes them very, let's say, risky in the sense that they could change from one year to the next quite a bit. You might have a great year one year, and then you have a terrible year the next year, but this is the actual 90% confidence interval. This is the final result. So the logic is that while we're pretty sure, I mean, that's our best guess of the mean, but we're 90% confident that the actual value of mu is somewhere in this interval. Let me actually add that to the next slide. So our best estimate, X bar, of the population mean, mu, is 8%. Okay, fine. If that's what we calculated, that would be the end of the story, but we are 90% confident that the true value of mu is between negative 2.4% and 0.184. So that's a big spread, okay? But that's the way the stock is. Oh, one more detail. As far as notation or terminology goes, rather, think of this as the lower limit of our interval. And this is the upper limit. Now, we're still allowing for the possibility the mean could actually still be higher than 18.4% or lower than negative 2.4%, but it's just not very likely. It's very possible. I mean, you never know with samples. We may have inadvertently chosen a sample that contains all the highest returns or all the lowest. It's possible. It's just not likely. You know, it's like, imagine if, like, let's say with this class, I decide I want to do a little survey, and I want to know on average how far away you live from the school. And well, there's only 16 people in the class, but let's say I choose a sample of 5, and I accidentally pick the 5 people with the longest commuting times. Well, my sample mean is going to be really realistically higher than the true population mean because of the sample that I chose. And it's also possible that I've chosen the 5 people with the shortest commuting times by accident, and that could give me a distorted view as well. So there's always a chance that our sample mean does not really reflect the population mean, but the chances of it happening are pretty remote, let's face it. So, but not impossible. So that's what this is really all about, giving us the mean, but also the range of possibilities. Now let's jump ahead to 95%. Now, if you notice carefully, the only thing that changed is the z-score. There's only one difference right there. Now, also notice that the margin of error is higher. Before, it was only 0.104. So with a higher z-score, we have a higher margin of error, and the range of possibilities is even wider. X bar hasn't changed. What's changed is the margin of error. Okay, so the margin of error increases as well. And the interval becomes wider. All right, that's an important detail. In fact, I'd like to summarize this in the next slide. And we'll prove it with the next one. When we get to 99, you'll see this once again is happening as the confidence level increases. The z-score increases. So the margin of error also increases. As a result, the confidence interval gets wider. In other words, in order to be more confident in our results, we must include progressively more values in our confidence interval. So in other words, if you want to be more confident in your results, you have to allow for a wider range of values. And that's what's happening. But specifically, it's because when we keep increasing that confidence level, the z-score goes up, the margin of error goes up, and of course the interval has to get wider. But the logic is that to be more confident in our results, we have to include more values. All right, like just as a quick example with the commuting time. For example, we are 95% confident that our mean commuting time is between 25 and 35 minutes. In order to be 99% confident, we must include more extreme possibilities. For example, the interval might increase to 20 to 40. Okay, in other words, if I want to be 99% confident, I've got to include that one time that it took 40 minutes to get to school because of the traffic, or that other time when the weather was so beautiful that it only took 20 minutes to get there. So I need to be expanding the size of my interval if I want to be more confident, because then I'm including progressively more extremely large and extremely small values. All right, so let's do 99%. You'll see the same pattern continues because the z-score jumps up to 2.576. And once again, this is our 99% confidence interval. And the only change is right here, the z-score. And of course, it got bigger. So the margin of error, look how high it got. It went from 10.4% to 14.4, all the way up to 16.3. Now look how wide this interval is, somewhere between minus 8.3% and 24.3%. So that's a lot of uncertainty. That indicates that this stock is very, very, very risky. You might not want to buy this one for your portfolio. So you know what I'd like to do? Let me just quickly summarize. Oh, sorry. Let me just put that back for a minute. I'd like to summarize all three of them on one slide so you can see them all together. I like that idea of having them all together in one place. You can visually see how wide they get at different levels of confidence, at least for this example. All right, so give me a minute to catch up, and then I'm just going to create a new slide. And also, once again, if you are using the TI 83 or 84, you can actually save yourself some time by using its built-in functionality. And all the instructions are here in the slides if you want to use them. If you're using another calculator, well, I don't know which one it is, but I just keep using the 83, 84 as an example because it's been my experience that many high schools require this calculator. And you may just have one. If not, it's no problem. But if you do, you might as well take advantage of it. Okay. So all those instructions are here, but what I'm going to do is summarize this. So that you can visually see them all together. So 90% gave us all right, let me grab that. Just so that it's all together in one nice location. So you can visually see that what's changing in each case is the size of the margin of error. And that, of course, causes the interval to get wider. And the reason, of course, is because the z-score is getting bigger. In fact, you know, let me just quickly remind you here. Okay, that should do it. Everything is together in one place. All right, now it's completely all set. You're all good. Okay, so now we're ready to learn the second case where the population standard deviation is not known. So remember, there's only the two cases we have to worry about when we're constructing confidence intervals for the mean. So let's go back and review that for a second. If we're estimating a confidence interval for the population mean, there's two possible cases that we could encounter. This one. Now, obviously, the other case is that sigma is unknown. Okay, but when that happens, it turns out that we can no longer use the standard normal distribution. We need a new distribution, which we haven't seen before. So we're about to learn a brand new probability distribution, complete with its own table. In fact, here it is right here. For the first time, we're introducing the so-called t distribution, and this is the corresponding t table. So luckily, this one is easy to interpret because if you look in the bottom, it contains the words confidence level, so you can easily find what you're looking for. Okay, so we'll look at this in a second, but first, Case 2 is the case where we do not know the population standard deviation, which of course means we're using the sample standard deviation instead. Where is it? Here we go. Okay. So if sigma is unknown, we use S instead, the sample standard deviation. Now look at this formula. It's very similar to what we had before. Just a quick reminder, I sneaked it up there so you can still see it. What's different here? This is the new piece. We now use the so-called T distribution. The T distribution, which is brand new. And if you notice, it has two values that we need to take into account. Alpha over 2, this part hasn't changed, but this superscript n-1, n is, of course, as usual, the sample size, but the role of that is something we haven't seen before. So we're going to introduce ourselves to the T distribution, and then we will carry on from there. Okay, so in other words, we have to do a little detour here. We must understand what this is before we can do anything. All right, now the T distribution actually has a very interesting history. Most of the results we have in statistics were developed over the centuries by mathematicians. Although in most cases, they were developed for a very specific purpose. Not always. I mean, some of these distributions were derived just because they were interesting to somebody. But most of the time, statistics is really geared towards being used to describe what happens in the real world. Now, in this particular case, the T distribution was not invented by a mathematician. It was invented by this gentleman named William S. Gossett at the very beginning of the 20th century. So this is a very new development in terms of statistics. The normal distribution has been around since at least the 18th century. So this T distribution is a bit of a newcomer. And it was developed because there was a need for it. Now, who was this guy, W.S. Gossett, and why did he need this distribution? Well, he was actually the head of what's called quality control at the Guinness Brewing Company in the early 20th century. Now, quality control is a branch of management where your job is to make sure that whatever product you're making is of consistent quality. Of course, you can't sell products without making sure that they have a consistent quality. Otherwise, you're going to go out of business. And now, of course, this is 100 years ago. And interestingly enough, talking about quality control, I actually saw a documentary fairly recently about Wise potato chips. And they go inside to the factory in this documentary to look at how the potato chips are being produced. And you may not be shocked to hear that almost none of this work is done by human beings. They have all these elaborate machines that basically do all the work. They have a machine that peels the potatoes. They have one that, cooks the potatoes. They have one that cuts them up into slices. And the interesting part is that at the end, when the potato chips are just about ready to be put into the bags, and they've been salted, they've been cooked, everything's done, but they're ready, just about ready to go into the bags. Before they go in the bags, there's one last step. They go through this machine that uses laser beams to analyze the color of the potato chips. Why do they do that? Because this is the easiest way to find the ones that have been burned. Okay, it's not uncommon for a lot of the potato chips to get overcooked because they're cooking them in very hot oil, and sometimes they get burned. And so the purpose of this machine is to make sure that none of the burned potato chips gets into one of the bags. So the laser beams are set up to catch the ones that are too dark. And the ones that are too dark, they go down a different tube in the machine. It has two tubes, the one that lets out the good ones, and the other one sends the bad potato chips to the garbage can. And so that machine is actually performing quality control for Wise potato chips. It's looking at every single one of them with a laser beam, and the ones that it doesn't like get thrown into the garbage can. The rest of them go down the other tube or chute into the bags, and then they're sealed and then they're delivered. So quality control means that they're trying to make sure that none of the potato chips that escape from the factory are burnt or have any other issues, like too small, let's say, or not crispy enough. But apparently the light is enough to tell which ones are good and which ones are not. Now, here's Gossett 100 years ago. He doesn't have access to all these wonderful machines. In order to make sure that the beer is being produced correctly, realistically, the only thing they can do is taste it. The problem with that is that if you taste too much of the beer, you're going to have less to sell to the public. So they were hoping to find a way to basically ensure the beer had the highest possible quality without drinking it all before they sold it to the public. So he was interested in analyzing the properties of small samples. In other words, they would randomly pick a certain number of the beers and make sure that everything was normal before they put them in the cans and then sold them to the public. The problem with this is that at the time Gossett was working at Guinness, there was no probability distribution that was appropriate for studying the properties of X bar when the samples were small. Now, you might recall from our discussion about the central limit theorem that in order to ensure that whatever we're doing, these samples are normal, either the population has to be normal or else the sample sizes have to be at least 30. What if neither one of those conditions is met? What if we're working on something where we're not sure if the population is normal and we also have sample sizes less than 30? Now, when we were talking about this in chapter 8, I just said, well, we'll have to do something different. Now we can find out what that something different is. We can use the so-called T distribution, which Gossett invented in order to deal with these small samples that he had. And so it was created for the express purpose of studying the properties of small sample means. Now, by the way, interestingly enough, sometimes this distribution is known as the student's T distribution. What happened with Gossett was that he published a paper in one of the really prestigious statistics journals where he presented his results. And, people said, oh my God, this is fantastic. But his name does not actually appear in the article. He put his name down as student. So why would he do that? Well, because before Gossett arrived at Guinness, his predecessor had apparently been involved in industrial espionage, stealing secrets and selling them to rival beer producers. So the company said to Gossett, listen, you can publish, but you cannot use your own name and tell anyone that you're working at Guinness. So, if you're going to publish a paper like this, make sure nobody finds out who you are and that you're working for Guinness, because again, we don't want anyone to know what we're doing here. We have to protect our trade secrets. So he publishes the paper with the name student. And ever since then, it's been called either the T distribution or the student's T distribution. Now, everybody knows that now that it was Gossett, but at the time he had to keep it a secret. Otherwise, he wouldn't have been allowed to publish the paper. Now, what we want to do is understand what this T distribution is all about, and we'll discover pretty quickly that it has a lot in common with the standard normal. So what was the purpose of creating it then? Well, the big difference between the two, let me just write this as a separate slide here. The most important difference between the T distribution and the standard normal distribution is that standard deviation of the T distribution, which means, of course, the variance, is significantly higher. Well, all right, is higher than for the standard normal distribution. In other words, the whole idea here is that what separates the two is that the t distribution has a larger standard deviation and variance, and that's really the main difference. You'll see it when we look at the graphs. So the properties are this. Now, first of all, the t distribution is continuous like the normal. It is symmetric about the mean. The mean is 0, and it's a bell-shaped curve. So far, it sounds like it's exactly the same as the standard normal, and it is. But the most important distinction here is that you can think of it as being more spread out. The t distribution has more area in the tails and less area near the mean. So let me try to draw a little sketch of this real fast, so you can see what I'm talking about. Let's see what I can do here. So here's our standard normal. And the t distribution might look like this, let's say. All right, it's not the best, but it's okay. This will do the job. What I really wanted you to see, actually, maybe I can adjust it a little bit. All right, so what I wanted you to see here is that, first of all, this is the t distribution, and this is standard normal. If you notice, the t distribution has more area in the tails, but less area in the middle. But more area in the tails, they're called. So you can see it's not that different. It's just that the t is more spread out, let's call it. The t distribution than the standard normal. Other than that, they're basically the same thing. I mean, you can see they're both bell-shaped curves, they're both symmetrical, have a center of 0, but the t is more spread out. And that is needed to capture the increased uncertainty associated with smaller samples. Okay, notice the logic here is this. And we've already discussed this in chapter 8. Smaller samples, with smaller samples, the means can be much different from each other. With larger samples, the means are likely to be closer to each other. Okay, in other words, with small samples, you can have a very big difference from one sample mean to the next. With the large samples, not so much. The t distribution captures the additional uncertainty associated with the means, small samples. Okay, that's what it's for. Now, here's an interesting side note. Based on the central limit theorem, as the sample size approaches 30, the t distribution and the standard normal distribution are almost identical. With smaller samples, the two can be very different. Okay, so in other words, that there's that magic number of 30 again. Once we hit 30, we really don't have to use the t distribution any longer because the two are essentially the same thing. But when we have very small samples, that's when the t becomes especially important. Now, here's a little detour too. I just want to remind everyone that the standard normal, the normal distribution all right, here's a little, stimulation to your memory. The normal distribution is a class or family of distributions, each with its own unique value of the mean and standard deviation. The standard normal distribution is the special case where the mean is 0 and the standard deviation is 1. All right, I just want to remind you of that because the same thing is true with the t distribution, except that it's a little bit different than what you're seeing here. Because the t distribution can only have a mean of 0. So how can we distinguish from one t distribution to the next? Unlike the normal distribution, what I should say is like the normal distribution, the t distribution is a class or family of distributions. Unlike the normal distribution, the mean is always 0. What separates one t distribution from another is the sample size used to generate it. And the parameter that is based on the sample size is known as, now this part, I do not know the origin of this word, this phrase, but we're not going to think in terms of the sample sizes, but the so-called degrees of freedom. I do not know where that term comes from, but with the t distribution, we're introducing this new concept called degrees of freedom, which basically reflects the sample size that we use to create this distribution. The reason why we're doing this is because in some applications, the degrees of freedom might be equal to the sample size -1, it might be -2, it might be -3. In other words, each case is different. So we're going to think in terms of this notion of degrees of freedom. And when we're now, by the way, when we are specifically constructing confidence intervals about the population mean, the degrees of freedom is always equal to n minus 1, okay? So remember that. In this chapter, the only case we'll ever run across is the degrees of freedom for this t distribution is equal to n minus 1, which is the sample size minus 1. In other applications, that might be different. But here, when you see the words degrees of freedom, just think of n minus 1. And in fact, I'll tell you what, you know how you can tell? Because if you go back and look at this formula we started to look at earlier, oh, there you go. That's what that n minus 1 is for. That represents the so-called degrees of freedom. So it's a reminder that your degrees of freedom is n minus 1. All right. So again, now, by the way, once we get the hang of this, you will never, you'll never get confused. It sounds like so much to worry about and think about, but in reality, what you really have to do is figure out how to look at these t values in a table. And the rest of this is exactly the same as what we did before. Now, by the way, here's something, what I did was because this is so hard to draw properly by hand, I went and got a computer program and I said, listen, let me draw these distributions side by side. Now, here we've got the case where we have the blue is the t, the green is standard normal. All right, so green is z, and blue is t, but specifically with 5 degrees of freedom. Which means that in this chapter, the sample size is only 6. And you can see they're pretty close to each other, but as we said before, we have more area in the tails. And less area near the mean, which is of course 0 for both distributions. And the mean is 0. Okay, now what I'm going to do in the next graph is increase the degrees of freedom to 30. Remember, we did say that 30 is essentially the cutoff point between small and large samples. Once we hit 30, what you're going to see is that the two are almost identical. All right, so again, green is standard normal and blue is the t distribution. So I challenge you to see the difference in this one. All right, let's see. I'm going to show it to you right now. Oh my God, they're so close. You really can't even see it anymore. By the way, we often abbreviate degrees of freedom, as you can imagine, DF. The table will actually do that. And see, now they're almost the same thing. So what that tells us is that T is really most useful when we have small samples. That's really what it's for. It's like the small sample version of the standard normal. Okay. Oh, it's 11:18. So what I'm going to do next, and when we get back, we can say this for when we get back. The next step is to look at the moments of this distribution, and then we can look up some values in the table. Once that's done, the actual confidence interval problems will be easy. Okay. The challenge is really understanding how to look up the t-values. Once that's done, the rest is exactly the same as what we did earlier. Okay. All right. So let's knock it off for a bit here. And when we get back, we'll learn how to look up t-values, and then we'll do some examples with the t-distribution. And then we can switch our attention to the proportion case, which is really easy because with the proportions, you only use the normal distribution, which is kind of nice. All right, so let's stop for a bit. And when we get back, we'll carry on with this. All right, so first of all, we want to quickly look at the moments for this T distribution. Now, first of all, we did say that the T distribution is characterized by the degrees of freedom, so the moments will reflect that. Now, the mean, as we already know, is just 0. That's the easy one. Now, the variance, though, and by the way, this is supposed to be, this is a new Greek letter. It's called nu, and this represents the degrees of freedom for this T distribution. So the variance is nu over nu minus 2. Okay, that's the shortcut formula for calculating the moments, the variance of this T distribution, which of course means that the standard deviation is simply the square root. All right, so remember the mean is 0, the variance is nu over nu minus 2, and that of course means that the square root, the standard deviation is simply the square root of that right there. Now, by the way, this helps us understand why the T distribution is more spread out. In fact, why don't we do this real fast? Remember, we had the two cases. We had the graphs for the T distribution when degrees of freedom equals 5. The standard deviation would be 5 over 3. And so that equals approximately 1.29. Now, of course, you know that for the standard normal, the standard deviation is 1. But for the T distribution with degrees of freedom equals 5, the standard deviation is quite a bit higher than it is for the standard normal. And that's why, if you recall, the curve was more spread out. So let's go back to that, this one. The standard deviation for the blue curve is 1.29. It's only 1 for the green curve. And you can see what a difference it makes. It means there's more area in the tails. But again, there has to be less area in the mean, near the mean, because the total has to also be 1. That part never changes. The total area under both curves is 1, but the way the area is distributed is a little different. So if there's more area in the tails for the T distribution, there has to be less near the center so that the total is always 1. Now, if we jump up to 30, though, watch what happens. That, of course, means the degrees of freedom is 30. So therefore, this becomes 30 over 28 square root, and that's equal to approximately 1.035. Now that's still more than 1, but it's not much more. And if I keep increasing the degrees of freedom, then the standard deviation will get closer and closer to 1. Okay, so even at 30, you can see that it's only slightly higher, and that's why the two curves are so hard to tell them apart, because they're that close to each other. Imagine if I had 50 degrees of freedom, you really and truly could not see the difference. All right, anyway, now, as far as the table is concerned, let's just say as an example for the table, well, actually, before we even do that, let's go look at the formula again. And so of course, the challenge will be coming up with this number. The rest is exactly the same. So I'll tell you what, rather than just randomly looking at numbers in the table, why don't we do the first example and see how this works? We have a university with 10,000 students. That's our population. The GPAs are normal. A sample of 10 is chosen. The sample mean is 3.10. That's their GPA, by the way. The sample standard deviation is 0.25. Now, when you're given the sample standard deviation and not the population standard deviation, this means that you must use the t-distribution. All right, no matter what other information you're given, if they give you the sample standard deviation S instead of the population standard deviation sigma, that means you must use the t-distribution. That's how you can tell. That's the only way. If you read the problem carefully, you look at what version of the standard deviation they're giving you, that's how you'll know whether to use t or standard normal. Now, we're going to go ahead and do all three confidence intervals, 90, 95, and 99, just like before. So here's what we need to worry about. What to do with this thing. Well, now here, remember, alpha is 0.10, or alpha over 2 is 0.05. Also, in all of these cases, since n is 10, n minus 1 is 9, and that means we're using the t-distribution with 9 degrees of freedom. So I need two pieces of information to look up this number in my table, the degrees of freedom and the confidence interval that I'm constructing. So let's go get that table now. And we go to the bottom and look for 90%. If you look at the left-hand side, this column represents degrees of freedom. For God's sake. This happens whenever my finger hits the side of the thing. There's a little button on the side of this marker, and I can't stand it. All I have to do is lean on it, and this is what happens. All right, so in our case, we showed that degrees of freedom is 9. So there's degrees of freedom 9. Now, unfortunately, the labels are in the bottom. So that means this column is the one we need. This column combined with 9 degrees of freedom, where they overlap right here, is your t-value, or it can be called a t-score. Sometimes it's called a critical value. We can think of it as a t-score, 1.833. Okay. Now, while we're at it, why don't we look up the corresponding value for 95% confidence? Now, we have to move to a different column, but we'll be staying in the same row. 95% is the one right next to it. And so with 9 degrees of freedom, that jumps up to 2.262. Okay. And then finally, let's do 99%. It's the same row. This time, the column we need is this one. See, the 99 is right here. Oops. Okay. Jesus, what happened? Okay, I got a little sloppy there, but it's this column right here. And so we're looking at 3.250. Okay, so 9 degrees of freedom. And then for each different case, we look at a different column. The row won't change because it's 9 degrees of freedom. So that's 3.250. Now, you might think, well, why don't we just memorize these? Unfortunately, though, this is only true for 9 degrees of freedom. So you can't really memorize these. The Z is different. The standard normal, there's just the 3 and that's it. Here, there's 3, but they will be different for different degrees of freedom. So you can't really memorize these. Or if you can, your memory is a lot better than mine, that's for sure. So for this particular case, these are the 3 t-values, or t-scores, you can call them, or sometimes they're called critical values. And now the rest is just plugging into this equation. Okay, so let's do that. All right, so remember, n is 10 in these cases. So you've got your t value here, because this is 90%. N minus 1 is 9 degrees of freedom. So we looked that up already. These you're just plugging in the numbers you have. And so we end up with an estimate, or X bar, and we have a margin of error. And so let's see what that turns out to be. So normally what you do is you calculate the margin of error first, which in this case happens to be 0.1449. And of course, this is X bar. And this is our confidence interval, the lower limit and the upper limit. Now here, if you notice, the range is pretty tight. Unlike our example with the stocks, here the range is quite small because the margin of error is very low. It basically means the students have very similar GPAs. Okay, so that's our 90% confidence interval. What will change in the next case for 95 is, of course, this t value, or t-score. It goes up to 2.262, and of course, as a result, the interval gets that much wider. All right, so this is now 95%. And that's where this comes from. The rest, we just plug them in. But you can see already the margin of error will be bigger, and therefore the interval will be that much wider. Okay, so, and once again, I'm going to put them all together in one chart, one slide, so you can see them all together. All right, so when you do the calculations, you're going to wind up with here we go, margin of error. And this is our result, lower and upper. Just a quick reminder up there. And then for the third part, with the 99% confidence interval, once again, the only thing that changes is the t-value. It goes up, and therefore the interval will get a little wider. Let's take a look. Here we go. Yes, it did get wider. Or will, you'll see when we do the calculations. Okay, so let's see how that turned out. Yeah, there we go. So the new margin of error is even that much larger. And there's our X bar, and that's our interval. All right, so I think it's time to put these together on one slide. Once again, just so you can see how much of a difference it makes between 90, 95, and 99%. All right. So we'll start with 90%. All right, so that's 90. Let's do 95. And 99%. Okay, just so you can see what a difference it makes between 90, 95, and 99. And of course, in each case, the margin of error gets bigger and the interval gets wider. Now, one more thing I wanted you to see. Let's go back and revisit the t-scores. All right, so what I want to do is make up a chart. Just I want you to see something very important here. Hold on. What we're going to do here is compare the t-scores and the z-scores when we have 9 degrees of freedom. So for this one, we have 2.262. So what am I doing here? I just want you to see, actually, make some room here. The z-score, sorry, the t-score is always larger than the corresponding z-score. Because the t-distribution, as we saw earlier, is more spread out and has a larger standard deviation. So no matter what values you're choosing, your confidence interval, and no matter how many degrees of freedom you have, the t-score will always be larger than the equivalent z-score. Just, I just wanted you to notice that. All right, then. So now it's time to move on to the proportions. Now, up to this point, every one of these cases, we were constructing a confidence interval for the population mean. That was what they all had in common with each other. I didn't, let's see, I must have mentioned it here somewhere, but now we're going to use the proportion. And what's going to be different here is that when you're dealing with the population proportion, we never use the t-distribution. Okay, so this is what the formula looks like now. And as you can probably guess, this on the right-hand side is our margin of error. The P, as you recall, is the sample proportion. And N, of course, is the sample size. And of course, Z is a Z-score. Alpha is the same, so that part hasn't changed, but with these cases, you'll never need the t-distribution. Okay, just want to point that out. So it says it right here. There's only one case. When constructing confidence intervals for the sample proportion, the standard normal is always used. We never use t-distribution with proportions. There's a reason for that. Actually, hold on one second. Let me slide this back in case I want to make sure you had time to write this down. The reason for this is because we've discussed this already. Proportions can be thought of as following the binomial distribution, because let's say you're thinking in terms of what proportion of the population is left-handed. Well, everybody is either left-handed or they're not. Let's face it. There's only two possible. I mean, realistically, we can think of everyone as being a lefty or a righty. So the proportion is essentially following the binomial distribution, but we already know that we can always use the normal distribution to approximate the binomial, at least if we have a reasonably large number of trials rather. If we only have a very, very small number of trials, then we probably wouldn't do what we're doing here. We would use the binomial, but as long as we have a reasonably large number of trials, we can use the normal distribution instead of the binomial. And that really does make things a lot simpler. So unless we have an unusually tiny sample size, this procedure will be perfectly valid using the normal distribution. Okay, so that's why we're not going to use the t-distribution, because the binomial converges to the normal, not the t. All right, so now the rest of this isn't much different. We're going to we'll look up the correct z-score, plug it in here, figure out the margin of error, and then we'll have our confidence interval. So it's very straightforward. Okay, so let's just say that we have a random sample of 105 fast food restaurants, and we discover that in 74 of these, they have at least one vegetarian option. Okay, some of them actually have salads, for example. It's not all fries and burgers. They have salads. And so X represents the number of restaurants with the option to have a vegetarian dish. 105 is the sample size. So our sample proportion of restaurants with the option is about 70.48%. Yeah, I mean, in recent years, they've all tried to at least offer a few healthy choices, not that many, but, McDonald's, although I think for some reason during the COVID, they got rid of their salads. I don't understand the reasoning, but there must have been something, I don't know what. I didn't ask them. Whenever I've been to McDonald's recently, I've asked about the salads and they've said, no, we don't have those. No explanation. They just don't. But it's because of the COVID. I just don't see the connection, but there must be a reason for it. Who knows? Maybe COVID attaches itself to lettuce. I mean, I guess the way to look at it is that at least the burgers are being cooked. If there's something in there, the cooking will kill it, but not so much a salad. If you have salad with something wrong with it, it's not going to get cooked. So I guess they feel it's safer to just only offer items that are actually cooked. I guess with the ice creams that they're so cold that it would also kill whatever happens to be in there. Yeah, it turns out that bacteria, there's a small range of temperatures at which bacteria can live. If anything is too hot or too cold, it just kills them. And in fact, that's part of the reason why food is cooked in the first place. It's not just for the taste, it's just to kill any bacteria that happens to be in there. Okay, enough of that. It's getting very strange, but anyway, so the proportion that offer a vegetarian option is in the sample 70.48%. We want to use this information to come up with a confidence interval for the actual proportion in the entire population that offers a vegetarian option. So now this part we don't have to worry about. We already know how this works. 90% means the z-score is 1.645. 95, 196, and 99%, remember, was 2.576. So with that in mind, here is our formula. And so what do we need to know? Well, we've got the sample proportion here. 1 minus it here. Here's n, and here's z. So it's just a question of plugging in numbers. And of course, we have to figure this out, and then add it and subtract it from 0.7048. And we're all set. Okay, so on the next slide, it shows the actual results. Okay. And so the margin of error is not that high. It's only about 8.72%. And there's our final result. So the true population proportion is, we believe, it's between 61.76% and 79.20%. Beautiful. Now for 90, oh, wait a minute. You know what? I just realized I completely goofed it up. That was 95. I accidentally scrolled all the way down to 95. Sorry about that. Yeah, this was the 90% case. Whoops. Yeah, I goofed. This was 90%. So this is 90. Okay, sorry about that. And so the final result, after you plug these in, let's see, what is that equal to? Here's my margin of error. And of course, that makes this the lower limit and the upper limit. Okay, and then I accidentally did 95% already. So again, remember, the only thing that changes is the z-score, which raises the margin of error. And so we've already seen that that's this case. And then lastly, we have 99%. Remember, that z-score is 2.576. So we plug that in here. God, what is it doing? And this is, of course, P, 1 minus P. This is N, and this is P. So you can, as you can guess, the interval size will be a little bit wider as a result. Okay, so when you plug that in, this is your margin of error. And the interval is a little bit wider. So again, I would like to put them all together in one convenient location. Just so you can see them all together in one convenient location. And then, 99%. Okay, and there it is, all in one nice convenient location. And this had nothing's changed. This will be true for any confidence interval that we construct, by the way. As we get to the larger confidence levels, we always have a larger margin of error and the interval gets that much wider. Nice. Now, there's one last thing we want to consider in this chapter. Imagine the following scenario. Now, you can see the margins of error depend on what the level of confidence is, but what if we need to work this backwards? Let's say we are working in quality control and the margin of error, we do not want it to go above a certain level. And so, before I even forget, I want to mention one more detail here. Otherwise, what follows won't make any sense. In order to reduce the margin of error for any confidence interval, the sample size must be increased. Okay. So let's just go back and revisit the formula for, let's say, sigma is known. We can grab both of these, actually. And I'll get the other one as well. All right, I lost my place. Oh, here it is. Here it is. Okay. Now, I just want you to see mathematically why this is true. So if you notice, n is in the denominator of this formula. So if n increases, sigma over radical n and s over radical n decrease. And that means the margin of error shrinks. So it stands to reason. I mean, the more confident you want to be with your results, the bigger the sample has to be. It's like with the driving example. If you only took a sample of 1 week, you never know what that week was like. It might have been the worst weather we've had all year. It might be a really nice week. But if you took a sample of 100 days, well, then, let's face it, the reality is you're going to have a much better idea of what happens on a regular basis. So when your sample size gets bigger, there's less uncertainty about your confidence intervals. So why does that matter? Because sometimes, depending on what we're doing, there might be a limit to how large our margin of error can be. So especially in quality control, suppose that we are working in quality control and want to ensure that we can be 95% confident that the, let's say, contents of each bottle of Coca-Cola average 1 liter with a margin of error of 0.01 liters. Okay. Anything larger than that is unacceptable for whatever reason. Let's just say that if it's more than that, we have to change the way we bottle the sodas. So what we would like to do then is ask ourselves the following question. How large a sample size is needed to ensure that the margin of error is no more than 0.001. That's what we're about to address. In other words, what we're going to do here is we're going to say, instead of given with a particular sample size, what is the margin of error, we're going to flip this around on its head and say, what sample size do I need to achieve a maximum margin of error? Now, the formulas turn out to be surprisingly simple. So let me show them to you. Now, for the population mean, what we're going to do is this. Now, we're not going to actually use the t distribution because using the z in these cases is close enough. Okay, it's been determined from experience that this is close enough. So you can see the formula is you take your z-score and square it, you take your standard deviation and square it. E is the margin of error, okay, that we're aiming for. Okay, so E is the margin of error. This is what we're choosing. And so with all that being said, we can plug these numbers in and come up with the appropriate sample size. Now, by the way, in most textbooks, you would think there would be a separate formula with an S. We don't normally see it because this, even though this case technically assumes that sigma is known, this formula has been found to work well. So we don't need to have a separate formula for smaller, for the small sample case. So in other words, we'll always use this example. Now, here, for example, a retail chain wants to estimate the mean amount that each customer spends in its stores at a 95% level of confidence. They find that this population standard deviation is 10, and that they want the margin of error to be no more than 2. What sample size must we choose to make sure that the margin of error is no more than 2? Okay, well, look how easy this is, because first of all, when we have a confidence level of 95%, that means that the z-score is 1.96. We don't need the negative. The standard deviation was given to us as 10, and the error that we're trying to maximize it to is 2, and that gives us a sample size of 192.08. Now, obviously, we can't have a sample size of 192.08. So what we normally do in these cases is we always round it up to the next integer. We don't round the way you learned in high school science class. Anything from 0.49 down, you lower it down, 0.5, you go to the next integer. Here, we always go up, okay? So in other words, in this case, the correct answer would be 193. Always up, okay? Because that further reduces the margin of error. So this way we can be guaranteed that it will be no more than 2 and probably less. You can see this was not a complicated thing to do. I mean, look at this formula. It's so simple. As long as you know this piece from the confidence level, the rest is just plugging in and you're solving for n. All right, now what about proportions? Is there a separate formula for proportions? Why, yes, of course there is, except that instead of having the standard deviation, we have the sample proportion. So here it is. E is the margin of error. Once again. And of course, n is the sample size that we're solving for. All right, let's do an example. The same retail chain wants to estimate the proportion of customers that use the chain's credit card for their purchases at the 90% level of confidence, which of course means that the z-score that we need is 1.645. Now, we also determined that the sample proportion is 0.25 and the margin of error is 0.02. That's the maximum that we're willing to accept. So let's plug in the numbers. It's that simple. Okay, so we got a z-score, we've got a sample proportion, we've got a maximum margin of error. We plug everything in, and it turns out to be 450.19. And since it's not an integer, we're going to round it up to the next integer, which is 451. Okay, now that's it for chapter 9, by the way. So we should probably start working on the chapter 9 problem set sooner rather than later. I'll figure out what would be a good day for it to be due, but we definitely need some practice with this. But I think you'll find that once you just do a few, it's really not a difficult process at all. Okay, you just have to make 1 or 2 decisions and then you're done. All right, it seems very complicated, but it really isn't. Okay, I don't know, there's really only 3 basic formulas that we have. You just have to decide which one is appropriate. Now, obviously it's getting very, very late, but I just want to show you what chapter 10 is all about. We'll start that tomorrow. It's kind of like an extension of this. It's basically a different way of getting at the same results that we're seeing here. it's called hypothesis testing. And you've done this sort of to a certain degree, possibly in science classes in high school. A hypothesis is something that we're testing. We're trying to find out if a particular piece of information is correct or not. You might, for example, start out with the hypothesis that the average age of all the people in the US is 29. And then you set about trying to figure out if that's true or false. So this one is it's a multiple step process. And it's a little bit more complicated than confidence intervals. But again, once you get the hang of it, you'll find that it's really not that difficult. But there's several key terms that we have to learn. And we have to understand the steps that we're following, but you'll see the overlapping between the two chapters when we're done. All right, so also in this chapter, we're still using both the normal and the t-distributions. And we're going to apply this to means and proportions. And well, let's just say that, again, it'll seem shockingly complicated at first, but once you've done it a few times, you'll realize it's not that difficult. Okay, so all right, I guess we can knock it off here. And so what you should do maybe between now and tomorrow is maybe flip through these slides to get comfortable with what's coming. Because like I said, there's a lot of terminology in the beginning. But once we get over that, the rest will be pretty down to earth, especially because it has a lot in common with the previous chapter. Anyway, so yeah, you can see I'm re-explaining how to look up z-scores and t-scores, and but then there's new stuff in here too. All right, so why don't we stop right here, and we'll pick it up tomorrow. And so when this is done, all that really needs to be done is the sample final, which will cover 8, 9, and 10. And so because we do have the rest of this week and next Monday, I'm confident we can get this all done in time. So I'll let you know how late you can hand in the sample, the actual final. Probably you'll be able to get a few extra days past the day of the sample, I'm sorry, the midterm, but we'll discuss that tomorrow. Okay, so are we all set? All right, so I hope this didn't scare you too much, but you can see we're coming down towards the end, and it is getting a little more intense, but believe me, once you've done a few examples, you'll be all set. All right, so if there's no last minute questions, I'll see you all tomorrow.
Hey, Professor, I had a quick question, but
Okay,
this is more related to the Chapter 7 set.
Oh, okay. Is there something strange about it?
So not particularly. So I'm looking at number 2, like number 2A and 2B, and it says,
okay,
what's the probability for more than 30 inches or more than 35 inches? So I'm looking at it and I'm like, should I put it in as 35 minus 30 for the z-score, or should it be 36 minus 30?
No. Remember, with continuous distributions, there's no distinction made between these two.
Okay, all right. So it should be 35 minus 30
yes,
divided by 5.
That's right, yes.
Okay, that's how I did it, but I was like,
okay, good, yes.
And then I looked at
that was a very good
myself.
question, by the way. That is an excellent question.
Okay, cool. And then I had one question on the, I guess the midterm. It's not really, I don't know. So let me see if I can pull it up real quick. For which one was it? Give me a second, sorry. Number 11. It's like, what is an example of a discrete probability distribution? Do you want like an actual example of it?
Well, we learned about 2 of them.
Right. Do you want like a pick one of those 2 and
yeah,
write an
exactly.
example, or just ask?
No. Just literally pick one or the other.
Okay.
Yeah.
So it doesn't have to ask. I don't actually have to make like a sample problem. I just need to pick one of the other ones.
Just pick one of the 2 that we learned about.
Got it. Perfect.
Now, I mean, keep in mind too, this test that you're seeing here originally was intended for an in-class exam. And so some of these, you can literally just look them up in your notes, and that's fine, right? Because you're still learning as you do this. But I mean, it was just I'm just trying to find out, do you remember which ones are discrete and which ones are continuous?
Yep, makes sense. All right, perfect. Thank you.
Yeah. Okay. All right, anyone else? Okay, good. So I'll see you all tomorrow then. Oh, here's a chat. You're welcome.